Greetings, everyone. My name is Haochen Xia from Zhejiang University, and I'm thrilled to present our recent research to you today. This study was carried out in collaboration with Jingfei Liu, Jianlou, Zhanqing, Kui Ren from Zhejiang University, Yang Cao from Hokkaido University, and Li Xiong from Emory University. Our work primarily focuses on developing the S-sharp value to address the data valuation problem with the constraint of the right to be forgotten, along with relevant algorithms. Let me introduce the background for you. First, our research is under the background of data market, and we heavily rely on two concepts, Sharpe value and the right to be forgotten. Sharpe value is a notion from conceptive game theory represents a unique allocation of payments that satisfies all requirements in payoff allocation fairness. They are balance, symmetry, zero element, and activity. Balance is the payment is fully distributed among all data owners, and symmetry is equal marginal contribution results in equal payment. Zero element indicates that no marginal contribution means no payment. Activity means different games can be additive together. The right to be forgotten is a concept from data protection regulations. Data owners should have the right to erase their personal data from service providers such as companies and institutions. Furthermore, ML models trained on priori datasets are regulated, as this model might infer the training data. As a solution, machine learning has emerged with the goal to comply with the right to be forgotten with minimal overhead. A prevalent method for exact machine learning is to share shard data, training a constituent model on each data shard. Subsequently, all these models collaborated with using a specific aggregation strategy for predictions. However, this introduced complexity in data valuation. One of the challenges faced is inconsistency of the Sharpe value over the sharded structure. When data owners cooperate with a sharded structure in model markets, traditional Sharpe values struggle with payoff allocation. Specifically, the Sharpe value of a data shard doesn't equal to the sum of its data owner's Sharpe values. Moreover, computing the Sharpe value or its existing variants such as beta Sharpe, Cis Sharpe, and data Benzef value is the Sharpe complete task. When data owners opt out and seek to erase their data, previous valuations become obsolete due to the shift in data distribution. Our object is to address these challenges. First, we formalize the concept of data sharding cooperation through the representation of a sharded structure. This structure is depicted by a series of partitions over the whole dataset D. Like the example given in this slide. Z1 and Z2 are put in the same data shard, and Z3 is put into another data shard. Then we further refine the properties of the Sharpe value, making it adopted for collaboration involving data shard and the sharded structures. We introduce P1 sharded balance. The total payoff is fully distributed to all data owners, and each shard's payoff is further distributed among its data owners. P2 sharded symmetry. Shards with the same contribution receive identical payoffs. Similarly, data owners with matching contributions within a shard are compensated equally. P3 shard is 0 elements. If there is no contribution to the overall models, the data shard got no payoff within the shard. If the data owner doesn't contribute, they receive no payments. And P4, activity is not changed. Is the same as traffic values property. According to the property P1 to P4, we introduce the S-traffic values. This involves considering all potential collisions of data shards to value contributions. Our approach is top-down in terms of payoff allocation. When allocating payoff from layer 1 to layer 2, that is L1 to L2, the properties of balance, symmetry, zero element, and activity transforms into their sharply counterparts, but limited to each data shard. Therefore, we must also contemplate all potential collisions of data owners within their respective shards based on query sharded structures. To understand better, let's consider the S-sharp value. It's a extension of the Sharpe values. Given a sharded structure, some collisions or permutations becomes redundant for the S-Sharpe value due to previous collaboration. As the illustration, for S-Sharpe value, the permutation Z1, Z3, Z2, and Z2, Z3, Z1 is can be ignored. However, it is crucial to note that calculating the S-sharp value is the Sharpe problem. Consequently, if we stretched approximation algorithms such as Monte Carlo sampling, utility sampling, and paired utility sampling to approximate the S-sharp value of Z1 to Zn, or we can say it's Zi using Monte Carlo algorithm. We can uniformly sample valid permutation over the whole data set and determine marginal contributions by incorporating data points Di across all preceding data points in the permutation. Finally, execute the above steps k times and output averaging marginal contributions. And we found that using marginal contributions can be inefficient because it ignore to reusing evaluated utilities. As the slide shows, although the marginal contribution can only be used for SSV3, the utilities can be used SSV1, SSV2, and SSV3. So only use the marginal contributions is not efficient, and we want to maximize the reusability. So we propose the utility sampling. It has the main difference is it select a position to cut off the permutation and evaluate the corresponding utilities and use this for all related SSVI. Furthermore, we use stratification to make the variance small. In case of data removal request, recomputation from scratch becomes inefficient. Instead, we advocate the use of priori values to expedite the approximation process, employing techniques like the delta-based algorithm for individual or multiple data removal requests. In detail, the motivation for the delta-based algorithms is that when the data change is not obvious, the S-sharp values change can be small. So according to Hofstede inequality, we can approximate the change more easily. the workflow of the database algorithm is that we uniformly sample a valid permutation and then scan the permutation to evaluate the utility change by adding the deleted or we can see that the data set need to be removable. That is the P, and the P's corresponding data shard record this utility change for each corresponding data point. Then we use the similar stratification mechanism to evaluate the utility change for each SSVI. Finally, we will use the change of SSVI with the priorly computed SSV to generate the new SSV. However, the former delta algorithm is only for one removal request, and remove the data set is the data set P, and we want to remove more data sets, and in other words, we need to deal with multiple removal requests in a single batch. So we propose the batch database algorithm. The main difference is that we compute the utility change by removing the data sets that appears in the selected partial permutations. And it can be proved that this algorithm can also result the unbiased estimation of new SSV. And for implementation, we employ GPUs to accelerate the aggregation. Our experiments have indicated that SRP value can provide deeper insights into essential data within a sharded structure in specific scenarios. Furthermore, our proposed algorithm have demonstrated efficiency. Thank you for your attention.